So in section 2.2, we're going to be looking at the elements found in living systems. And our first learning objective is going to be to relate the atomic structure to the periodic table of elements, which means we need to know how to interpret and use a periodic table. And then list the important elements found in living systems. Now, this first point here says that the periodic table displays elements according to valence electrons. Not necessarily. It will if you know how to interpret the periodic table. First of all, the periodic table arranges all the elements in order of increasing atomic number. Okay. And remember that atomic number is going to be the same as saying the number of protons. So it's the number of protons which determines, remember the number of neutrons can vary from the last section. It's the number of protons that determines the number of electrons, right? And so what we're really going to be interested again is valence electrons. Now valence electrons is going to be equal to the number of electrons in the outermost energy level, which I mentioned in the last section. So now I'm going to tell you how to determine the number of valence electrons just by looking at the periodic table. So I'm going to go ahead and skip forward real quick here, and I have a small periodic table. And what we're going to do is we're going to ignore for now these metals that are here in the middle. These are the transition metals, and we're going to look at the first, second columns of the periodic table, and then we're going to go on over here to the 13th, 14th, 15th, all the way up to column 18. Now, sometimes they number these, or they call these the A block or the main block elements, ignoring the transition metals down here, and then these heavier metals further down. Sometimes they're given, they give these Roman numerals. This would be 1A, 2A. Instead of 13, this would be Roman numeral 3A, 4A, 5A, 6A, 7. So this would be, for example, 7A. So 7 would be a V with 5, 6, 7, and then an A. And then the last one would be 8A. So it would be V, 5, 6, 7, 8, and then A. So this would be the 8th column in the main block elements. So now if we understand that, this is going to help us determine the number of valence electrons right away. Now if we look here in the first row, which is also called a period, hydrogen is going to have an atomic number of 1, because it's arranged in order of increasing atomic number. That means 1 proton. So for here, you're going to have 1 proton in the nucleus, and that means 1 electron in the shell outside. So what I want you to do is to remember back where we have our nucleus, where you have the number of protons and the neutrons. And then in the first energy level, where you can find electrons, it holds a maximum of 2 electrons. In the second energy level, it holds a maximum. Let's move back here. Should hold a maximum of 8 electrons. And the next one's going to hold a maximum of 18, but we're only going to really be concerned with it holding up to 8. So for now, let's just go ahead and go with 8 electrons. Once you fill up, you got to start filling the lower levels first. Once you fill up those electrons, then you're going to go to the next energy level or shell until you get those filled up. Now when we're going to fill in these electrons, we can draw them with dots. And this one is going to max out with 2, so I'm going to draw 2 dots separated as far apart as possible. The next one I'm going to start drawing them 1, 2 as far apart as possible, then 3 and 4, and we can still fit 4 more because it fits up to 8. Now I'm going to go back and pair them up, and if you pay attention to that pattern that I used to fill them in, it's very important because it's going to help us draw dot structures later. The same thing on the next level. Once we fill with 8, then we go 1, 2, nope, we don't put that one there. Okay. It's not erasing, but we would go 1, and then we go all the way across 2, 3, 4, and then you go back and start pairing them up. 5, 6, 7, 8. And now we filled up completely all of those energy levels, okay? Now, if we started with hydrogen, we would only put one dot in that first energy level. So for hydrogen, I'm going to draw the electrons for each energy level separated by columns. So for hydrogen, one proton is only going to have one electron in this valence shell. It would go right there in that first energy level. If we go to helium, which is the next one, it can fit, it's going to have two protons, so it can fit two. So the first two electrons would fill up that first energy level. So I'm going to put a 2 there. If I go on now, and I go to the end, and I come over here to lithium, lithium is going to have a total of 3 protons. That means we would start putting our first 2 electrons in the first energy level, 1 and 2, and now we're only going to have, we don't have any more space for that third one, so it has to go to the next energy level. So I'm going to draw it 2 in the first level, 1 in the next. Okay. And so what I want us to do now is go and see and try this now. We would keep following that pattern, for example, for beryllium. For beryllium, beryllium would be, has a total of 4. It's atomic number 4, 4 electrons. The first 2 go in the middle, in the inner level. It holds a maximum of 2. And then we start filling in the next one, but we only need 2 more to total to 4. Okay. And then if we went and we tried this, so let's keep moving on. We would follow this pattern. Let's go ahead and go ahead and try this for fluorine, for example. Okay. Fluorine is the 9th element. The atomic number, if we could read it right up there, I would say number 9. There on the periodic table. The 9th element has an atomic number of 9. Okay. And so I don't know what happened here to my... Okay, so I had to go back and redraw these. They disappeared on me. So remember that down here, this is your nucleus in the middle that contains the protons and electrons, and trying to draw the representation of the electron structure. Remember that the inner energy level holds a maximum of 2, the next one 8, and the next one we're going to say holds 8 even though it's 18. And if we went to fluorine, and fluorine has an atomic number of 9, it's the 9th element there, then we have to have 9 protons, and that means 9 electrons. The first 2 go in the first shell, that's 2 there, and we still need 7 more. Now the next shell can hold a maximum of 8, so we're good. So the arrangement would be 2 in the first one, 7 in the second one. So it would be 7 drawn in that next level there. Okay. Now if we did this for neon, neon has an atomic number of 10. So again, 10 protons in the nucleus, that means 10 electrons. So that would be 2 in the first level. And 2 out of 10 leaves 8 more. And we can fit all 8 because the second energy level is at 8. And so there you go. So now if we go to sodium, here's where something significant comes about. Now sodium is the 11th element, so it's atomic number 11. That means 11 protons in the nucleus, which means 11 electrons in the energy levels outside. So that means there's going to be 2 in the first one. That leaves 9 more. The next one can hold 8. So that's a total of 10. We need 11 electrons. So where does the next one go? The next one's going to go into the 3rd level. So that means only 1 in the outermost level. Now we're following along here. And we do this for just one more element to see the pattern that we get. Chlorine. Now chlorine is, we're going back to where fluorine was in the same column over here. Chlorine has 17 electrons altogether because it's going to have 17 protons. Remember the number, atomic number in the periodic table tells you the number of protons, and then you have to be neutral, so you have the same number of electrons, 17. The first 2 go in the first energy level, and we've maxed it out. The next one is going to get 8. Now that's a total of 10. But we need 17, so that leaves 7 more. And the next, or the 3rd energy level can actually hold those extra 7, or those last 7. So now if we look at fluorine, and we look at chlorine, and they're in the same column here, which is column 7A from earlier, right? We're at the 17th column. Notice the last energy level, the outermost energy level. You notice how both of them hold 7? That's the outermost energy level, which is your valence shell. If we did this for bromine, iodine, anything in that corner, the electrons are going to fill in the innermost shells. Once you get to the outermost shell, guess how many they're going to have? 7. So that's 7 valence electrons in that column there. We can verify this pattern of column being related to the number of valence electrons by going back and looking at all of those in the first column. Now, hydrogen only has 1 electron, and that means its outermost shell has only 1. The next element is lithium, and lithium has just 1 in its outermost shell. And then we did sodium over here. Sodium is also in the first column, and if we fill in those electrons for sodium, all 11 of them, we see that the outermost shell has only 1. Okay, so all of those in the first column have 1. If we did this for all of those in the beryllium column, they're going to have 2 valence electrons. Again, we're going to ignore the transition metals in the middle for now because that's more complex chemistry. How many valence electrons would this one have? 3 in the boron group. Carbon would have 4. Now, carbon has 6 electrons altogether because 6 protons, but we're talking about the number of valence electrons, those that are in the outermost shell. Nitrogen would have 5, oxygen would have 6, all of those in the second to the last column would have 7, and then we get to 8. An exception, though, is helium. Helium doesn't even have 8 electrons. It only has 2 protons and 2 electrons. But what is it that all of these in the last column have in common? Is that their electron valence shell is full valence shell. And most of them get full with 8. We're going to call that the octet rule. The exception is helium, and it fills up at 2. Remember that innermost shell right there? Fills up at 2. So what's common to all those in the last group? They maxed out their valence shell. And when you max out your valence shell, your outermost shell, you don't want to react with anyone. So all of the other elements are reactive because they want to be like the last group where their valence shell is full. In fact, they call this last group the noble gases because they're noble to each other. They don't react with anything because they're stable. All the other ones are unstable unless you get the octet rule, unless you get to the octet or duet like helium. So that's something to remember. So now when we go back and we interpret what it says here, the valence shell is the number of electrons in the outermost energy level, we can now go back to this periodic table and say, hey, we can tell right away, first column is 1 valence electron. Second column, they all have 2 valence electrons, and so on. And this makes your families of elements that behave a certain way. All of those in the first column, for example, they're called the alkali metals, and they're highly reactive metals. Very, very reactive. It turns out they lose that valence shell very easily and give off, which makes them very, very reactive. The ones in the second to the last column only need 1 more to fill it up, and that makes them very reactive because they just need to get 1 more in there. That's pretty easy for them to do. Okay, so this brings up the idea of the inert or non-reactive elements. Those are going to be in the last column. I called them noble gases just a while ago. And all of them have 8 valence electrons except for helium, but it's also noble gas because it's filled up its innermost shell. So we're going to be following, when it comes to trying to predict what kinds of compounds or reactions we can make, we're going to be following the octet rule. And that means that all of these atoms are going to tend to want to do or become noble by trying to establish an octet or get 8 in their valence shell. When they do that, they become more stable. Okay, so that's where we're headed with this. So here's a periodic table looked a little bit differently. You can see those columns raising out towards you from the screen. And what they're doing is these columns are coming out towards us to show their relative abundance in living things. So it turns out living things are made of a lot of water, which is H2O. And so this is showing column-wise by mass the number or the main important elements that we see in the human body. Those that are in green are the more abundant ones. And we can see a list here of those elements that you see. The most common ones that make up our organic molecules are going to be carbon, hydrogen, oxygen, nitrogen, or what I like to call chun. So proteins are made of carbon, hydrogen, oxygen, and nitrogen. Nucleic acids, your DNA, they're made of those things. Carbohydrates have carbon, hydrogen, and oxygen. Fats, carbon, hydrogen, oxygen, and so on. So those are the main elements, and these other ones are going to be found in smaller amounts and are important for a lot of the processes go on inside our cells. This is another way to represent it, and what we've done here is this dashed line represents that middle group I said to ignore earlier, the transition metals. It's just showing the first two columns. We're ignoring the middle here, the transition metals. We're ignoring those. And the last 6 columns over here. So there's a total of 2 columns here and 6 here, a total of 8, which adds up to 8, like the octet rule. So here in your group 1, and then what they did was they drew the electrons in those energy levels. Remember, these are not orbits. These are energy levels. The first energy level, and then the second energy level. And then if you look at all of those in the first column, hydrogen, lithium, sodium, potassium, and so on, and you look at the outermost shell, only 1 electron. So 1 valence electron there. Here in group 2A, those have 2 valence electrons, and all the way down. And then we come over here, like I said earlier, those in the 7th group are going to have 7 if you counted them. And then over here, all of them except helium are going to have 8. So neon has 8 on the outside, argon has 8, krypton has 8. It's the valence shell that's very important. In the group 7A, fluorine group here, all of those are going to have 7 valence electrons. Now what I'd like you guys to do is to start getting used to drawing just a simple dot structure. And all that dot structure is going to do is represent the elements. You put the element symbol and just draw a dot for the valence electron. For all of those here, so for example, lithium, which in group A is going to be, you're going to put Li with 1 dot, right? So example, lithium, 1 dot. In the second group, they're going to have 2 valence electrons, so we're going to draw the symbol. I'm just going to put X for the atomic symbol and draw 2 dots. Example here would be, let's take magnesium. You would draw its atomic symbol and then draw 2 dots. Be able to draw dot structures for these. Okay. For these right here in the third group, it's going to be the symbol, like boron, and then put 3 dots. Okay. For a carbon, for example, put the dots as far apart as possible. You draw it like that. Okay. So for example, carbon would be 1, 2, 3, 4. Remember, carbon or any other element, they're going to have more electrons inside, but we're only interested in drawing the dots for the valence shell. So practice doing that. How would you draw phosphorus? Phosphorus, like nitrogen, is supposed to have 5. So it's 1, 2, 3, 4, and then now you can go back and pair up. You can start pairing up anywhere you want. So phosphorus, nitrogen would look like this. So practice drawing those. For sulfur or oxygen, you're going to have 6 valence electrons. Remember, there's electrons further in. But if this were oxygen, you go 1, draw an O, and then 1, 2, 3, 4, 5, 6. Right? So for sulfur or oxygen, you draw the symbol 1, 2. Again, draw them as far apart as possible. 3, 4, and then go back and start pairing up 5, and then 6. Okay, that's the way you would draw the dot structure for sulfur. For chlorine, I actually drew one earlier in an example. 1, 2, 3, 4, 5, 6, 7. And there you see 7 valence electrons. You can tell right away how many more does it need for an octet? 1 more. So it's got space for 1 more. Those here in column 6, group 6, those still need 2 more electrons to get that octet, right? Now for all of those, the exception is helium. Helium would only be drawn with 2 dots. Everything else here is going to be drawn with 8. 1, 2, 3, 4, 5, 6, 7, 8. And we're full. So for example, neon would be drawn as 1, 2, 3, 4, 5, 6, 7, 8. Be able to draw dot structures for these group A elements. Okay, that's an expectation, and then we're going to use those to show how chemical bonding occurs in a future section. Now, the periodic table that we've been looking at, there's 90 naturally occurring elements, but if you count them up, there's more. This is because scientists have figured out how to make artificial elements. There's only 12 elements that are found in living organisms in significant amounts, and I pointed out those to you earlier. Remember, they were over here. So that list that you see here, there's 12 right there, and some of them are very important in making up your organic molecules. So 4 elements are found made up of the most part of our weight, or 96% of that, and that includes carbon, hydrogen, oxygen, and nitrogen. So just remember which one, right? There's also some trace elements. Those are going to be found in really, really small amounts. Some of them are not even listed here. For example, vanadium would be found here, and that's not on the list. Sodium, chlorine, calcium, these are going to be found in smaller amounts. For example, phosphorus is important in making DNA. Sulfur is going to be found in some proteins, for example. So be familiar with those. And always remember that C, H, O, and N, carbon, hydrogen, oxygen, nitrogen, those are the main ones found in the most abundant by weight in our cells. And then some of these other ones like sodium and calcium, phosphorus, those are important either for making other molecules or for running your metabolism within your cells.